Well, thank you very much. First of all, thank you very much for inviting me to give a presentation. Secondly, sorry I could not be there in person because of a recent operation, so I can't fly. So I apologize for that, but hopefully the content will just be as good, and then you don't have to actually see me in person. I will be providing a copy of the slides, and also there will be a video recording of this presentation. So again, it's something that may be useful for you in the future. So moving into the presentation, first of all, a little bit of background. I've been involved as a manufacturing engineer all of my working life. I've been involved in contract manufacturing. I've been involved in printed circuit board manufacture. And for over 30 years now, I've been running training courses just like this one, online or hands-on in factories. So that's just a little bit about my background. So first of all, we want to talk about voids. And during the previous presentation, you will have heard about vacuum soldering. And I'll mention it slightly from my own experience. But basically, voids is a cavity. It's a hole in a solder joint. And it's been around for many, many years. And with different types of technology, we've seen different types of voids being present. And I illustrate here intrusive reflow book that I wrote a couple of years back. You can get voids in this sort of technology as well. But it's not really a major issue. So we'll look at the issues, we'll look at how to solve it and improve process issues, but really voids in many cases are not really an issue. So if we talk about voids, what we want to try and do is visibly see them. And now with X-ray technology and also video, we can actually see inside joints as they're being reflowed. And this is just an example of voids you can see on the left-hand side of the screen actually being visibly seen during X-ray inspection. And on the right-hand side, you can see pretty much the same thing. And what we're looking at is the solder paste reflowing, and you'll see again evidence of voids. And when you move on to your presentation on X-ray a little bit later on today, again this will be explained in terms of inspection techniques in a little bit more detail. But this again just gives us the ability to simulate a process. Now, what I've done here in this list is just given you a checklist of some of the things that you should consider when you're trying to eliminate voids in production or voids at a contract manufacturing facility. And please, there are the obvious ones, the obvious issues, and then there's the less obvious issues. And I will try and demonstrate those to you during this presentation. But first of all, I have to step back quite a few years when I was actually requested to make voids, and I've made voids successfully in through-hole terminations and in surface mount joints. It's a little bit more difficult to create them in BGA and area array packages, although I have successfully done this on a couple of occasions. And just to illustrate on the through-hole and surface mount terminations, each of the photographs I show here I created myself, and the reason for this, I didn't agree with doing it, but I was asked to do it, is to produce visible samples which were of a consistent size. And the way I did this was with stainless steel wire, actually in the solder joint as the solder reflows and then solidifies. So you've got a standard void size visible from the outside during visual inspection. Not suggesting you guys need to do this, but it's just something that I had to do as a boy, a young engineer. So if we look at criteria for a moment, X-ray criteria has become available in the last few years, but when I started X-ray inspection and BGAs early or the end of 1990s, I created my own standard because there wasn't anything. And you have to have something to train people to. So the criteria I show you here is what I produced in 2000. So that's 19 years ago. And if you look at the numbers, it's not a lot different than most companies have been working to over the last few years. Now we have IPC, and we've got criteria defined there. But just so you understand where it all came from, and if you ever see any of my own standards, you'll know that, you know, I created them before anybody else, I'm pleased to say. Now, there is one other document which was around, and this was the Belcore standard. And again, we're talking about many years ago, but in that standard it said that voids cannot be anything greater than 1%. Now, in the real world, you can't measure 1%, and with the greatest respect to any X-ray company, this was just virtually impossible to do. But it was crazy that anybody had a standard like this to start off with. But then again, some people that write standards don't actually work in manufacture. Now, criteria today, we have IPC, and the majority of companies worldwide work to IPC standards because it is the most well understood document. And if you look at the latest version, we've got criteria for voids within solder joints, which is great. If you look more carefully into the documentation, really the criteria talks mainly about collapsible joints. So this is BGA's area array packages where the solder ball becomes a liquid as well as the solder paste during reflow. Unfortunately, it doesn't really talk about non-collapsible solder joints. So there's criteria which exists for the traditional area array packages, but not for non-collapsing area array columns and balls, which really there should be detailed criteria for. So what I'm talking about in this instance is the ones I've highlighted in these X-ray images. So on the left-hand side of the slide, you're looking at a traditional BGA, ball grid array joint that's reflowed successfully. The bottom image is a QFN, and on the right-hand side, you can see I've circled non-collapsible joints. And these are where the solder is becoming a liquid and reflowing and wetting to the pad and also the pin or the ball. But the ball and the pin, in this particular case, is a high-temperature alloy which will not reflow. So we're actually just talking about voids in those locations when we're assessing joints. So just to understand what the different types of terminology and types of problems that we might see are. Now, in addition, there's a NASA standard that you might like to review. It's free. If you do a search online, you can find this. And this talks about 10%. Which, in my opinion, is too low in the real world of manufacturing, but it exists. In addition, you may be familiar with the European standard, the European Space Agency standard, and this still sits at 25%, so 25% voids. This was defined, or the assistance was defined by work that was actually done by the National Physics Laboratory in Teddington in London through trials they conducted with ESA. Now, I said that we had a list originally for things for you to check, and here I've expanded a little bit more on the list, and I've picked out a couple of things which really I don't see as a major issue, but some people have done. Voids on packages when you receive them. I've honestly never seen this on any packages that I've examined for customers. So I don't really believe that you're actually getting the voids originally from the manufacturer, and I'll justify that statement a little bit later on. And some people used to say that we get a lot more voids with lead-free than we do with tin lead. I kind of tend to disagree with that statement. It's during the transition to lead-free technology, people were still learning how to use the solder pastes correctly to get the best performance, and that was at the time when people were looking at voids. So consequently, perhaps with a poor understanding or not a good understanding of the process and materials, we were still learning, so we saw more voids. You don't tend to see that differentiation in manufacturing today. So we'll try and pick up on these points as we go through our presentation together. Now, first of all, if you can see a problem happening or understand how it happens, you're a lot closer to solving a problem. So this is why I like to do process simulations. So rather than actually looking at the end result, I like to try and understand what's happening. So these two video clips just show what's actually happening during the reflow cycle of solder paste on a PCB underneath a glass slide. So we're simulating what is a component sitting on the surface. And you can see on one view, the bulk of the void is staying in place, and on the bottom view, it's not present. And this is and can be related to the material, the paste, the activity of the paste, and the gases produced during the working of the paste. Flux and cleaning and oxide formation help to create voids. So understanding why some materials react better than others is a very useful exercise. So wherever you can look at something or simulate it, break the problem down, I think that's extremely valuable, and it's not difficult to do. Now, voids that come from design features. Now, these are a couple of examples of via in pad. So it's where we're putting a via in a pad during the design stage, and we can create voids. Now, there's two ways that voids are actually created in this situation. One, because of trapped volatile material, either air or part of the paste material. It's got no way to escape. You put paste on, you put a component on the top of it, it's got nowhere to go. The second one is where the via actually gases itself. So what I normally do when I'm looking at a problem for a customer, I break the problem down. So here what I'm doing is testing the vias and the pads for outgassing. And I use a special oil to simulate gassing. Now, I've been doing this for sort of probably over 40 years, testing boards for outgassing using oil. And you can see something on my YouTube channel to show how this is done, or alternatively, I can do this for you. But you can see gassing coming out from the surface, and what this does is prove whether it's a plating problem, a thickness problem of the plating in the via within the board in the first place. So again, that's fairly easy to do, to simulate to see what is the root cause of the problem, which is what we're always trying to understand in the manufacturing process. So if you look at this example, what I'm showing you here is a board, and these are plugged vias, and we're going through the soldering phase, but we're using oil as a medium to be able to show the outgassing. And I think this is dramatically obvious what's actually happening. I was actually working for a company trying to solve void problems, but I could prove that it was the board which was the issue and the design which was the issue to start off with. So try and break the problem down. Yes, you can find ways of eliminating voids in different ways, but if it's the root cause of the problem, which is the most important thing to look at. So if you look at joints, and particularly ones where you've got via in pad, this is often what you might see if you mechanically break the solder joint apart. And what I've done in this example, I've pried the component off of the printed circuit board, and you can see the void within the solder joint. You can see that there was a via in pad on the left-hand side, because you can see the outline of the pad with a hole in it. And there, where we've broken the joint on the right-hand side, you can see the void, which is just above the surface of the hole in the pad. Now, another way in which we can create, or we can see voiding, now this steps back quite a few years now, and originally on silver finish PCBs, it wasn't uncommon to see what we refer to as champagne voiding. This is hundreds of thousands of little voids. Now, unfortunately, I have experienced this more recently with an automotive supplier who was using tin finish on boards. And anyone who knows me knows that I don't like tin finish to start off with, but that's another conversation. So if you've got a surface finish, preparation finish on a PCB, and it can have organics, material within the surface of that plated layer, and you release them during the soldering operation, they can outgas only for a short period of time, but they tend to exhibit hundreds of thousands of very small voids. If you look on the left-hand side, this is just an example where I've broken a joint apart off of the surface, and you can see a lot of voids present. In this next example, again, if you look carefully, you can see the outline of round marks on the surface of the pad. And again, these are voids where we've broken the joint apart and pried it off the board so we can see this interaction. And what you would then do is take a board and test it for outgassing from the surface of the plating. So then you could prove whether it's a PCB problem, and although we can do other things like change the paste, change the profile, possibly use vacuum, it's overcoming a problem that exists to start off with, which is not what we want to do. We want to understand the problem first of all. So doing this proves it's the PCB, which is the root cause of the problem. These are two microsections that were done by McDermott, and I show these because I've never been commissioned to do x-rays of this type of joint. I've always just done the testing on the PCB. So again, a problem that did exist a few years back. I have seen it more recently, not on silver but on tin, so again it's something to be aware of. Now, when we reflow balls on printed circuit boards and we use flux, the ball becomes a liquid and we're soldering to the PCB as we would when we're creating BGAs in the very first place, and that's what you're looking at here. It is very uncommon for voids to form, and the reason being is that you've got bulk solder, you haven't got solder paste, which is going to coalesce together with the ball and release gaseous materials into the bulk of the joint. If you're just using flux-only reflow, it is much less likely to happen. And this is the reason why I say that it is unusual to actually see voids in solder joints produced by reflowing balls onto packages. So if you're reballing a package using flux or flux gel, or if you are making BGAs to start off with balls, then it is less likely to see voids in any examples. And it's also true that if you're reflowing high temperature balls, and these are examples of me reflowing high temperature, 90% lead, 10% tin, and these are what you would use on ceramic packages quite often. These do not become liquid during normal reflow. You are soldering to it. Now you can have voids in this situation because you're using solder paste, but they would be confined to the area around the joint. They wouldn't be in the bulk of the solder. And in all honesty, if you do mechanical testing, you are more likely to see a reduction in strength where the voids are present at the interfaces as opposed to in the bulk of the solder. Now, stepping back a few years, I used to make my own BGAs, and I actually still do to this day when I am required to do so. The reason being it's a cheap way of making BGAs. So I either print solder paste, I dispense or jet solder paste onto the PCB, I reflow and make joints in that way. Now in that situation, these are some of my Bob Willis homemade BGAs, yes you can get voids, and that's all about the paste and the process you're running. So if you're creating BGAs or you're adding solder to a package, etc. In this particular case, yes, you can get voids, and it's again down to the paste and the profile, etc. But I spent years making BGAs, and it works quite well, and it's a cheap way of making components, dummy components, for workshops and training staff in rework and repair. So moving over to a little bit to what we are looking at. Well, we've shown voids forming. We've talked about where they can form and what are some of the reasons voids form in the bulk of the solder. One of the important things, I believe personally, is whenever you're making a new product, you're building a new product for your customer, or you're building your own new product, during NPI, new product introduction, it is very important to capture as much information as you can. And what I'm illustrating here is just simply checking BGAs out during NPI build. So if you've built your product, and we capture the information, we make sure we measure void size and ball size and capture that information, because you're doing environmental testing of your product. So if you're testing your product mechanically and you find it meets your requirement, and you also have voids of 14 or 15% or 20% or whatever, you have got the data which proves that the product will be reliable even with voids of that size. You can then go back in the future, possibly, to show and demonstrate to a customer that you have done all this proprietary work. But if you haven't, then it's a bit more difficult. And it's fairly easy nowadays with modern X-ray systems to capture information that you can file away, which may be useful at a later stage. But also, if you're doing failure analysis, you've got the data to allow you to see what has changed in your process. So I always insist that I do this type of work when I'm doing an MPI, new product introduction build. So I've captured the information. And if you are subcontracting your product to a company, it's good practice for you to either gather the information yourself or get your contractor to gather the information when he's doing his MPI build. It's not difficult to do, but it's very useful as a point of reference in the future. Also, if you're changing solder paste materials or the company wants to change their process, again, you've got a point of reference. Now, concerns of voids, well, basically the standoff height of a component to board will change. So if you've got voids, inevitably that's trapped air adding to the bulk of the joint and the solder you had. So we'll give you a slightly higher standoff, which may or may not be measurable. The size of balls will be bigger, as I've already said. We are concerned potentially that it might affect reliability. And there's been lots of work done to demonstrate that voids, up to 30% don't really affect the reliability of the solder joint. It's really where it is. Now, again, a lot of people discuss about heat transfer. Now, I often get involved in talking about voids in QFNs. Now, the majority of QFNs never dissipate very much heat at all. So I don't really understand why we had the conversation in the first place, but that's another thing. You need to make sure that if you're working in manufacture or working in contract, you understand what the customer specification is. So if it's defined in IPC or a specific requirement that he has, that must be understood and defined. And if you can meet that requirement, then fine. If on a specific product you need to meet a higher standard, then you need to look at some of the things I've already mentioned to improve the void formation which is in the solder joint. If you can't change anything in your process like materials, print thickness, etc., one of the options, obviously, as you've already heard, is vacuum in vapor phase or vacuum in convection, just to mention convection as well. So those techniques are available, but they are there to overcome a problem where you can't change anything else in terms of your material set. So as I said, if you want information about reliability of joints, there are lots of technical papers, but there's also this particular document which is available from the NPL, which contributed to the document I mentioned earlier from ESA, the European Space Agency. So you can download that if you're interested after this webinar. Now, concern with voids, impacts of voids on reliability, I've already mentioned that really it tends to be at the interfaces, that's where more likely, rather than the bulk of the solder. It's because the greater stresses are normally seen at the interfaces as opposed to the bulk of the solder. So that's the areas that you may be particularly interested in looking at. Now, we've mentioned BGAs, and I've illustrated to you some of the things that cause us problems. I wanted to also incorporate why we see voids from other things. Now, if you see voids in other surface mount terminations, it's not uncommon, and particularly now with tin finish, to see outgassing from the component leads themselves. So what you're looking at here is voids in solder joints which will have a small impact in the mechanical strength, and I say mechanical strength, not reliability. It may just affect the mechanical strength of the solder joint, and it can be generated by the component terminations themselves. In this video clip, which I'm showing now on the left-hand side of your screen, look very carefully at the top of this capacitor. Don't look at the solder reflowing, look at the top of the capacitor. And what you're looking at is gassing from the plating of the component. And this is what is contributing to the voids in the solder joint. So the actual manufacturing process, the plating of components, can have an impact. If you look on the right-hand side of the screen now, you can see an example of a specific capacitor package that gave me a lot of problems with outgassing quite a few years ago. But mechanically, the solder joint would not fail. So we set criteria based on the void size or shear force of the component, and everybody was happy. If you look at the photograph on the right-hand side of the top, you may or may not say that's good or bad, but it's irrelevant because mechanically it certainly exceeded the shear force that you would normally expect a component of this type. So consider the other options. We've talked about the PCB surface finish, we've talked about the components, we've obviously talked about the process of assembly, but it's the other things which quite often can have an impact on void formation. Again, another few examples here, and these are either traditional capacitors, electrolytic capacitors, but you can see the voids present in the bulk of the solder joint. And these were all caused by outgassing from the component, not the actual solder itself. If you look at this video clip, you can see me literally just touching a soldering iron, and you can see the plating move and fizz. And that is what's contributing to the void formation in solder joints. Normally when a termination outgasses, it's only for a few seconds, and normally speaking it's at the top, the high temperature of the profile that it's actually occurring. So you may then be coming down in temperature at this point in your process on your particular product. But taking the component out of the equation and looking at it can be very valuable in overcoming the particular problem. Again, in this example, we're again looking at plating, which has in fact outgassed quite significantly, and it visibly looks appalling in terms of a surface finish, but that can be the reaction. In these two very simple demonstrations now on video clip, I'm just showing me doing a reflow and wetting of a plated pin, and watch this de-wet, and this is significant amount of de-wetting that you can see here. So that's a lot more obvious, and on the right hand side this is less obvious, but the same thing is actually happening on these connector pins that I'm reflowing again, and you can see the gassing, although quite small, on the surface, as the solder reflows, and this would contribute to lots and lots of very, very small voids in the surface at the interface, and these would be mechanically weaker in terms of any joint you actually produce. Now, a voiding presentation would not be complete without talking about plated through holes. Now, plated through holes we still use today with through hole components for hand soldering, selective soldering, intrusive reflow soldering, and 9 times out of 10, 99% of the time, it's all to do with the PCB. So this is just one of the simple tests that I've conducted many times to demonstrate to customers and videoed, as you see here. And you can see I'm just adding solder to the through hole joint, but you can see it's popping away quite nicely. And it will continue for the length of the time the solder is in liquid state. So on both of these examples, you can see it quite nicely popping away, and it's got nothing to do with contamination in the hole, solder mask in the hole, old boards. It is outgassing due to moisture in the printed circuit board and thin or poor quality plating in the printed circuit board. Those are the main reasons. Now, if you're talking about running this with an intrusive reflow soldering operation, then again we can get a similar reaction. But also, if we're just talking about voids being created in via holes. So on the left-hand side, I've shown a couple of photographs while I was talking, and you can actually see bubbles forming and then exploding. This is what we call balloon defects, where you've got a solder balloon on the top of the plated through hole, which may or may not pop during the soldering process. Now, if we move and just talk a little bit about QFN, these are just some reflow clips and just showing you what's actually happening when I'm doing process simulations of QFNs. And the main reason that we get voids within QFN packages during reflow, it comes down to the design of the printed circuit board, or it comes down to the design of the stencil. So when I'm trying to understand these process issues, what I tend to do is use optical simulation or X-ray simulation to see what's actually happening in the process. And this is a very powerful tool to be able to do that. So I said that too much paste, and the key thing here with QFN LGA packages is trying to reduce the paste volume under the center package area. And these are just examples of stencil designs I have used in the past to do this. And the ones at the bottom are to allow me to print onto the center area on the PCB, but not put paste onto or into the vias. That's the crucial thing. If you look at a good design, what we've got here is via in pad, which is fine, but what we should be doing is trying to put solder mask around those vias, but not fill the vias. The reason being that you don't want solder to go into the via, but also you want to use the via to allow the volatile material from the soldering process to escape. But those design features within the stencil allow some of the volatile material to escape during reflow, and that's also what you want. So if you have got via in pad underneath QFNs, that's fine. Put a resist solder mask donut around the via. Ideally, tell your PCB manufacturer to image it so you don't fill the via, so you've got both the opportunities. Gas to escape, but solder won't fill the hole, and that really works very well. And that's true of single row QFNs, or in this particular case, multi-row QFN packages during your assembly operation. Now, this is just a graph taken from a paper that I did with David Bernard many years ago, 2009 in fact, and the green line just simply represents the difference between boards that I produced with the resist donuts and ones I'd left open. So the red, the yellow, the orange show void formation. The green shows less than 5%, and that was because of the use of the vias in the design. That worked really, really well on this particular test. We've also done work on voids and standoff. If you measure voids and standoff, you will see a correlation between voids and standoff height, and this has also been highlighted by engineers at REM in some of their studies. So again, it's something that, think about, if we can reduce void formation, then that can be a benefit for us. Now we can also get voids due to squeeze out or depression, and this is over placement, where we've applied too much pressure. I always, when I'm doing setup, NPI build of products with bottom termination components, I always X-ray the boards prior to reflow to see the displacement of the paste. Because if the paste is displaced too far away from the pads, it can create other defects, but when the solder is trying to pull back to the pads, it can result in non-wetting of the pads, which then can also look like voiding within the bulk of the solder. Now I mentioned pin-in-hole intrusive reflow on a couple of occasions, and for those of you who know me know I'm a great fan of the technology. It's simple to do, it's very cost effective, and it works great in manufacture. But I do the same sort of thing when I'm doing this type of build. I inspect using X-ray. So here what I'm illustrating to you, I've already printed the solder paste. I've inserted the pin, as you see on the bottom right, but you can actually see how much paste, where it is after assembly of the component prior to the soldering operation. So it gives us an understanding of what's happening prior to the reflow operation. And if we reflow, this is just a video clip just showing the reflow process of a pin-in-hole intrusive reflow row of leads, and you'll see that the ones on the right-hand side reflow before the ones in the center of the connector, which is normal because the ones on the outer extremity of the component will always get up to temperature, reflow faster. But the point I'm trying to illustrate here is look at the voids within the solder as it reflows, and they are not always down to the paste. They can also contribute to voids specifically from the PCB outgassing. So again, this is just another way of illustrating that particular point. Of course, when you're doing pin-in-hole intrusive reflow, you will move on and do other examinations of solder joints, and voids is just one little thing that we talk about. So if we consider our different processes, I've illustrated here for tin lead technology and lead-free technology. One of the other things that's coming along, and there's a lot of interest now, is low temperature alloys, actually reflowing at below 200 degrees C. We can selectively solder with low temperature alloys, we can reflow and rework, and there's been a lot of work looking at this because it reduces energy consumption. There's lots of advantages. So in the future, there may be more companies looking at the use of low temperature alloys for reflow, and hopefully our experience of that type of technology may still show voids, but it certainly will reduce the temperature we have to use on PCBs today. Now, in terms of materials, I just thought it was useful to illustrate here. This is a study done by one particular paste manufacturer, and this relates back to fluxing and oxide formation and the generation of voids. So you can see here that this particular supplier looked at different makes or different builds, if you like, of SAC alloy, and what had an impact and what didn't have an impact. So this type of data is available from multiple material manufacturers, and it's something to ask the question about. If you want to look at paste as a way of reducing void formation, then it's something you need to look at with the alloy as well. So void reduction. few examples of vacuum now. You've already seen an excellent presentation on voids and vacuum, but I just thought I would obviously add my two penneth here. And these are examples, again, of a large transistor package. Top left-hand view is me x-raying prior to reflow, which I've already mentioned, I normally do. And then two examples, one of convection and one of in vapor phase with no vacuum. And we still got voids, but then when you reflow in vacuum with a properly defined process, you can virtually eliminate all voids. You've got to decide whether you need to, whether your customer wants you to, or from a reliability point of view, you need to eliminate the voids. And vacuum is a way of doing that. Now, one thing I would say, please listen to your supplier in terms of vacuum. In the early days of using vacuum, made a real mess, and I'm sure that the gentleman who gave the previous presentation will probably admit that he's done the same. If you try and pull a vacuum too fast with solder paste materials, you're pulling out the gap, you're pulling out the flux, you're pulling out the non-volatile material. So consequently, you can get component movement, splashing, solder balls, and lots of other defects, but it's only when you are trying to do things faster than is possible. Now, I know production managers want you to speed up your process. There is a limit. So please don't do what I do or have done. Please just follow the good instructions of your supplier if you are going to use vacuum with vapor phase or with convection. Another example, this is some trials I was running in Sweden, and I was building boards with different surface finishes, different pastes, and this is a typical example of X-ray. And then X-rays after a simple change to the use of a system with vacuum, so basically using the vacuum, and you can see here how the significant change here, and it was a simple change, how we've reduced void formation. Now, I mentioned a couple of times, and this is just some other data. Amcor did some work, and they looked at standoff height for different types of PCB technology, plugged vias, open vias, etc. And you can see here the effect of standoff height for those different design techniques. So I've suggested what I do, but I just obviously want to show what other people have done with paste coverage and via coverage as well. And also when we look at thermal performance, obviously every component that you use will be different, but this is just a comparison with one group of components where they looked at the change in power consumption for the particular device, the energy being produced, and voids and what impact it had. And you can see here that up to 50% voids underneath a specific package area had virtually no effect, and it was when you started to go above 50%. But when we're talking about voids, we're talking about 10, 20, and 30%, nowhere near 50%. So you need to understand what these devices that you're concerned about, which have voids in, what power dissipation they're actually having to deal with, rather than trying to overcome a problem which doesn't actually exist in the first place. Now, a couple of other examples of voids in other types of technology. This is with underfill. Some companies use no-flow underfill, and what I'm showing you here is outgassing from the solder resist, which does occur. So if you've got a liquid on a surface, as you would with an underfill, it can outgas during the heating and soldering operation. If you've got solder trapped within material, like a solder ball, and you have voids, look at how the solder can run around when it goes into a liquid stage. So it's just like a kid's sand worm farm, if you're familiar with that. So again, it's looking at the less obvious, and these are just some photographs of a trial that I was doing for a customer, and you can see the impact of voids and how it changes the shape of the solder which is in the actual underfill during the rework process. And you can see a short starting to form on the bottom right. And this is all to do with voids. So again, different types of voids, yes, but still the same old problem. Again, a close-up view of some more outgassing from solder mask and the laminate surface. Again, if you are using underfill or you're putting solder over the top of multiple terminations, this gassing could impact your soldering performance. So you've got to look at the water retention or moisture retention from the PCB. So again, I've listed here some of the ways in which we can reduce void formation. And I've tried to be as honest and as helpful as I possibly can, but please try and consider some of the other things to look at just to understand why we've got the problem, and if you can correct those, then that really does help the manufacturing process. So I've come to the end of the presentation, and what I wanted to do now is take any questions that you might have, and Soren is going to take control of the microphone at his end, and he's going to relay the questions. So basically, if you've got a question, if you just ask the question, and then Soren will relay the question to me, and I'll hopefully try and answer it.